Welcome to the Dynamic Learning Hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a live classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Want to get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
much interested in learning digital marketing course for a very long period of time, but I don't get a proper platform. And I enrolled in XLR course. It was really good experience. Our course has been taken by Mayur sir, and he was very good. Teacher. He's not only focusing on theory part, he's doing how real digital marketing works, and it was in total very good experience. I get so much of knowledge. Here they're not only focusing on study, they're also conducting different exams to test our knowledge, and as we are giving the exam, so to appreciate our work, they give certificates for the toppers, and along with the certificate they give hampers. Thank you, XLR.
Recently I was searching for digital marketing courses online in Google, and I came across XLR and I attended a digital marketing course which was for 15 days. My mentor Mayur helped me for attending these classes. So he is a very informative and helpful guy. In the course end, there is a exam which I topped. So I came to the XLR office in Bengaluru. This digital marketing course has helped my career and my skills to develop, and the certificate has helped my company to join. Thank you, XLR.
I came to know about this course from my college. Actually, for learning platform, this is very nice, and I learned from here ChatGPT and AI from online for AI generative and ChatGPT. We are using this technology more, and after finishing the courses, I came for collecting the certificate. I seen the classrooms and faculties. Classroom is very nice. After the completion of exam, they will give gift and certificates. Thank you, XLR, for giving these courses. I learned a lot of from this. I gained more knowledge from here, and thank you for XL for teaching us.
In Swami Vivekananda Institute of Technology College, development using Flutter, which was given to us by XLR Solutions. I came across this program through my college faculty, who told us about this program, that it is a very good course and you should enroll in this course. I felt really good about this course because they started everything basic point of view, that even if someone who doesn't know anything about Flutter or anything about mobile app development,
Good afternoon, dear faculty members. I see the people are joining. We'll wait for 2 more minutes, then we'll start for the day. The people are joining still, so we will wait for 2 more minutes. Okay, I hope we'll start. We'll start for the day. It's a good afternoon.
Good afternoon.
Yeah, you can take over the class, so you can start for the day.
Okay, am I audible?
Yes, you are audible.
Okay, fine. Okay, great. I'll share the screen. So, good evening, all. So today, we'll discuss from where we stopped yesterday, quantum computing basics. So yesterday we discussed about an introductory portion of quantum computing, and discussed about single qubit states. So yesterday I gave you a very introductory remark about what is quantum computing and what is the fundamental principles that drive quantum computing, such as superposition and quantum entanglement. And most importantly, what is the fundamental unit of quantum computing, which is a qubit. Similar to a classical bit in our computers and laptops, which takes values of 0 and 1. A qubit is an analogous entity for quantum computing. However, it takes 0 and 1 values simultaneously. That is the main difference of qubit from a classical bit. And this phenomenon is called superposition or quantum superposition. And another principle which defines quantum computing is quantum entanglement. And it refers to having two particles or two qubits, one sitting in my room and another one at far away distance, sometimes maybe in a satellite. And both of them are interlinked with each other, so that if I measure the property of this qubit, I can immediately know the property of the other qubit. So they are interlinked. And both of these properties are the key features of quantum mechanics, have fantastic applications and a lot of potential areas of interest. So ranging from biosystems where there is photosynthesis and modeling of this photosynthesis processes, and how the science behind the movement of the electrons within the pigmentations of photosynthesis. And similarly, other systems as well, like we can perform weather forecasting with greater accuracy, MRI scans, which uses quantum principles. Yeah, so that is about quantum principles. And we can also utilize this properties of quantum to discover new sciences, such as material science and engineering. We can model the Hamiltonian of different physical systems using the quantum gates and quantum operators, which helps us to discover new sciences. So as in any other field of study, quantum computing also has 3 areas to focus on. There is a theory, then there is a practical, and then there is a third one, which is about factual study, or knowing things factually, like in the news headlines. So anyone can, like a layman, can understand what is written in the news headlines, even if it's about quantum computing. However, all these three, like the theory, the practical, and the factual, all these three have a fundamental understanding, fundamental foundation. That is what we are focusing on this course, to build that fundamental foundation of quantum computing, so that we can appreciate both theory, experiment, or practical, and even we can appreciate more than news headlines which we read about quantum computing. So on that note, yesterday we had discussed. I'll give a little recapitulation. Yesterday we discussed about single qubit systems and what are these single qubits, how can they be implemented. I gave an example of electron spin, which can form a two-level system, and that can be leveraged to perform computational tasks, and how they are represented in the form of vectors in a vector space. However, when we multiply these vectors by a complex number, such as an iota I, both the representations point towards the same single cubic state, which means it's not a one-to-one mapping. So a better representation which has a one-to-one mapping is a block sphere representation, where we have a sphere whose north pole is a zero ket or ket 0, and the south pole is a ket 1. And all of the points on the block sphere are unique systems or unique single qubit states. And we can represent a relationship between the vector space and the block sphere as follows. So in the vector space representation, if I denote my single qubit state as ket psi, so ket psi is equal to, let's say, alpha times ket 0 plus beta times ket 1. So these are nothing but quantum states, but we can imagine them to be as vectors. So 0 and 1 are the basis states, and psi is a vector we are interested in. And that is a representation of our physical state. Just like we have an x and y vector space, and we represent a vector in this two-dimensional space with some coordinates. And those coordinates are basically the alpha and beta. And these are the peculiarity of quantum states are that it's a unit magnitude. It's of unit magnitude. So what does that mean? That means the alpha, mode alpha square plus mode beta square is equal to 1. So this is a vector space representation, and which we discussed it yesterday. And we can represent this in the form of a block sphere also, whose north pole represents ket 0, and the south pole represents ket 1. And any other point on the sphere can be represented as follows. Ket psi is equal to so this is cos. I want to write cos of theta by 2 okay, plus, I'll make space here, plus e raised to phi, e raised to I and phi. and sine of theta by 2. Now you can conduct a reality test here. So when theta, we know from the spherical coordinate system, theta is the angle measured from the z-axis. So if this is the state and this angle is the theta, and phi is the angle measured from the x-axis. So when theta is equal to 0, cos 0 by 2, it is equal to 1, and sine theta by 2 will be 0. Sine theta by sine 0 will be 0. And here I have missed an important thing. Here there will be a ket 0 here. Okay. And here there will be a ket 1. Yeah. So essentially it means the alpha in this case is cos theta by 2, and beta is e raised to I phi sine theta by 2. So when theta is equal to 0, I get ket psi to be equal to ket 0. And when theta is equal to pi, 180 degree pi, then I get this first term to be equal to 0 because cos pi by 2 is 0. And the second term will be e raised to phi is also 0 because we are just moving along this axis. So phi is 0 there. Okay. And sine theta by 2, sine of pi by 2, so it will be ket 1. So I get the south pole. So any general point, we can use this equation to find out in the case of a Bloch sphere. So now there is another representation for the quantum states, and that is a matrix representation. So I briefly mentioned it in the last session, that is yesterday, but I did not show this slide here. So it clearly shows you how we can represent each of the basis states, such as ket 0, ket 1, ket plus, ket minus, in the form of a vector, or in the form of a matrix. In this case, it's a one-dimensional column vector. I also mentioned yesterday that every ket vector, ket state, can be represented as a column vector and a bra vector, quantum state, like ket 0 or bra 0. Yeah, this is bra 0. It is represented as a row vector. So we can represent it as 1 and 0. And so we see that ket 0 is 1, 0, ket 1 is 0, 1, ket plus is 1 and 1. And why is it 1 and 1? Because it's a superposition state. Ket plus is equal to ket 0 plus ket 1 and divided by square root of 2, because we need the probability of the measurement outcome of getting 0 plus the probability of getting the measurement outcome of plus 1 to be equal to 1, and that is called normalization. And for that, we have divided it by square root of 2. And so if we see this is 1, 1, it simply means that there's a 1 by root 2 also here, I think. I have missed out the 1 by root 2 here. Okay, so if we put these values 1, 0 here, substitute these column vectors, and 0, 1 here, then I'll get ket plus. I do the addition like I do it for a normal matrix. So 1 plus 0, it will give me 1, and 0 plus 1, it is 1, and the 1 by root 2 factor. So that's how these states are prepared. So the assumption is ket 0 is 1, 0 and ket 1 is 0, 1. And from that we can derive the states for other basis states, such as ket minus will be 1 and minus 1. Why? Because ket minus is ket 0 minus ket 1. Okay, divided by square root of 2. And there are two other additional basis states I mentioned here. So these are just for bookkeeping I have mentioned. So these are eigenvectors of the y operator. So so it's quite important, quite equal. They have an equal standing with these other two states. So I mentioned them here because this is an eigenoperator for the z operator, and this is
Sir, actually, you're on mute, sir.
Yeah, thank you. So I was saying, sorry for the interruption. I'll share the screen. Yeah. I hope it's visible now, right?
Yes, it is visible.
Okay, thank you. So in the matrix representation, we have two concepts called inner product and outer product. So this is how we define the inner product. So we write the bra 0 and ket 0 side by side, and that is equivalent to multiplying the row vector by the column vector. And using the normal matrix multiplication, we find that 1 into 1 and plus 0 into 0, it gives me the scalar value 1. And same way I can do it for other cases like 0, 1, in which case I find that when I multiply 1, 0 row vector with 0, 1 column vector, I get a 0. What does it signify? It signifies that these two vectors corresponding to 0 and ket 1, they are not overlapping, or they are independent states, or in other words, they are orthogonal. So if I have two vectors in a vector space, x and y vector space, and if they have a 90-degree angle between them, I have one vector in this direction and the vector in 90-degree angle, then the dot product of these two vectors will be equal to 0. So same way, I have a bra vector and a ket vector of 0 and 1. They are having a similar situation of orthogonality, and thus they are equal to 0. The inner product is 0. Same goes with 1 and 0. It is also equal to 0. For 1, 1, I get 1. This is the same as I take a dot product of the same vector on itself, which is the square of its magnitude, and that's equal to 1 because it's a unit vector. Now we'll do a small exercise here. What about 0 and plus? Okay. So for 0, we have 1, 0, right? And for plus, we have 1, 1. So now what we do is simply we take the multiplication of the corresponding elements in the corresponding indices. Like here the first one is 1, here the first one is 1. And then sum both. So 1 into 1 is 1, plus 0 into 1, which is 0. So that gives me a value of 1, right? So yeah, so that's correct. 0 plus is equal to 1. And same way, what about 1 minus I? So why 0 plus is equal to 1? Why it's not 0? Why it's not 0? So like coming back to the block sphere here. So we find that 0 is here in the north pole, and where is plus? Plus is actually here, which is the x direction. So this is the z direction, and plus is along the x direction. Okay, so they are not orthogonal in this representation. We see that getting reflected here also. They are not orthogonal. Hence, I got a non-zero value. And for whatever 1 minus I, so here 1 is represented as 0 and 1, and minus I is sorry, minus I is 1 and minus I. Okay, so I get 0 into 1, which is equal to 0, and 1 into minus I, which is equal to minus I, and the answer is minus I. Right, so minus I is the answer for that. So that's how we uh, deal with inner products. But there is also another concept called outer product, and that's where we will come to this concept called tensor product, which is a very crucial mathematical tool to deal with not single qubit but higher dimensional such as 2 qubits, 3 qubits, and multi-qubits. Because when we deal with quantum computing, we are not always working with a single qubit, but we always need a multiple number of qubits, and that's how the problems are solved, and that's how the computational tasks are processed. So to understand, to work with that, we need to have this important mathematical tool, tensor product. And so consider two vector spaces, just like we discussed so far. There are two vector spaces, V and W. Each individual vector spaces have elements are the basis vectors A1, A2, AN for V, and B1, B2 till BM for W. And when the tensor product of these two vector spaces are taken, we get a new vector space having the basis written in this form: ket AI, tensor product ket BJ. And this I ranges from 1 to n, and j ranges from 1 to m. And there are a total of n times m basis vectors in this particular vector space, and that corresponds to an nm dimensional vector space. So this is a formal definition for this tensor product, and we will delve more into it today itself within a few minutes. But before that, we need to just brush through the properties of tensor product. So there are some common properties which are pretty easy. Like we have a situation where V1, one of the ket vector, plus ket V2, and this group is tensor product with ket W, then we find that the tensor product can distribute. It's the associative property. So ket V1 tensor product ket W plus ket V2 tensor product ket W. Similarly, we can write ket V tensor product with ket W1 plus ket W2. It can be written as ket V tensor product with ket W1 plus ket V tensor product with ket W2. If we multiply a scalar which is not a vector like A, then it can be equally, it can be there with W as also, or it can be written as a outside the bracket of ket V tensor product ket W. All three representations are equivalent. And lastly, if we have a situation where a bra V2 tensor product with bra W2 is dot product, it is the inner product or dot product with ket V1 tensor product ket W1. So this is a case where both tensor product or the outer product and the inner product both are there. So we get something like get V2, bra V2, get V1, because this acts on this, and the second one acts on the second one. So we have this get V1, V2, get V1, and get W2, get W1. And there's a simplified way of writing this when we are representing 2 or more qubits. Instead of always writing the complicated sign of tensor product, we can easily write it as get VW. So in the case where there are 2 qubits, one of them is in get 0, another one is in get 1, another third one is in get 0 again. And now if I want to represent a system of these 3 qubits, I will do a tensor product. That means I am collectively taking them, considering them together. So I do a tensor product of these 3 qubits. Instead of writing like this, I can easily write this as 0, 1, and 0. So this represents a 3-qubit system or a Q-trick system. And now let's solve a simple problem to check our understanding about tensor product. So the tensor product of the unit vectors ket V is a unit vector 1 by root 5, 1 minus 2, and ket W 1 by root n, 1 minus 3. So what is the tensor product? So now we are getting into a practical application of how we do it. So I have 1 and minus 2, right? So this is get V. And now this is multiplied with 1 and minus 3. So the constants are neglected for the time being. And we will add them in the end. So this corresponds to, I take the first element of the first vector, 1, and then I, so I take the first element and then I multiply it with the second vector, which is 1 and minus 3. Okay, and then I take the second element, which is minus 2. And then I, okay, I think I will, I'll just write this, the same thing here. Okay, so I multiply 1 with 1 and minus 3, and I multiply minus 2 with 1 and minus 3. Right. And what is the answer? So we get a larger dimension here. So what happens is in an inner product, I am when I do take the inner product, it results in a lower dimension. I'm getting a scalar from the vectors. But here I am getting the opposite result. I'm increasing the dimension here. So I get 1, minus 3, and minus 2 and 6. So what was earlier two-dimensional vectors, they when they undergo a tensor product, it results in a four-dimensional vector. So that is the meaning of outer product. So in the case of a multiple qubit system, we can represent them as follows: 0, 0, 0 plus 0, 0, 1 is a superposition of 0, 0, 0, 0, 0, 1, and so on, and other different permutations, and 1, 1, 1 finally. So what does it mean? It actually means 0, 0 means 0 gets 0 tensor product gets 0 tensor product gets 0. So there are two tensor products hidden here. but we write it simply like 0, 0, 0. And how many basis states are there for this 3-qubit system? So can you calculate that? So consider a 2-qubit system. I have 2 qubits in 0, 0, and then I have 0 and 1, 0 for the first qubit and 1 for the second qubit, and I have 1 for the first qubit and 0 for the second qubit, and I have 1 for both the qubits. So in total there are 4 states, right? 4 states, 1, 2, 3 and 4. So there are 4 states for a 2-qubit system, and that is equal to 2 to the power 2. Right. Similarly, for the 3-qubit system, I'll get a 2 to the power 3 number of basis states. What about n-qubit system? It is also called as qubits. So there will be 0, 0, 0 till 0 n. So these sub marks are written in order to identify them. That this is the first particle, this is the second particle, and this is the nth particle. All right. So there will be 2 to the power n basis states in total. Right. And there is an additional simplification. So we can also represent these states in the form of numbers, whole numbers. So we know from the binary representation, we can write as 0, 0, 0 n zeros as simply as 0. And when there is a 1 at the very end, which is the least significant digit, right, then it will be equal to 1. And if there is a if all of them are 1, and that will be a 2 to the power n minus 2 to the power n minus 1. For example, let's take n equal to 3. Let's say n equal to 3. So 1, 1, 1 corresponds to 1 is equal to 1 plus 1 in the second significant digit, that is equal to 2, and the third one is the 2 to the power 2, 4. So 4 plus 2 plus 1 is 7. So this represents ket 7. So this is equivalent to ket 7. So I can represent it in this way also for according to my convenience. Okay, so that is this representation. And I'll also touch upon matrix representation. I already discussed in the last slide. So here ket 0, 0 can be represented as outer product of 1, 0 and 1, 0, which are the single qubit vector representation, or simply the column vectors. And when they are when the zero product, then we get a 4-dimensional column vector, which is 1, 0, 0, 0. Right. Similarly, if I calculate the matrix representation of 0, 1, ket 0, 1, then this corresponds to the tensor product between 1, 0 and 0, 1, and that is, so this 1 multiplies with 0 and 1, that is 0 and 1, and 0 multiplies with 0 and 1, that is 0, 0. So I get 0, 1, 0, 0 as the answer. Let's try it out for 1, 0, ket 1, 0. What would be the answer? So here 0, 1 is representation for the first particle in the state ket 1, and second particle is in ket 0, so it is outer product, tensor product with 1, 0. Now the answer for this 0 multiplied with 1, 0 is 0, 0. So first two elements are 0, 0, and the second one 1 multiplies with 1, 0. So I get 1 and then 0. So this is the answer for ket 1, 0. And for ket 1, I have 0, 1 representation of ket 1, our tensor product with 0, 1. Again, the representation of ket 1. And 0 multiplies with 0, 1 is 0, 0. Whereas 1 multiplied with 0, 1 gives me 0, 1. So I get four different vector representations, 4 different column vectors. And these 4 can be used as a basis vector in the 2-qubit vector space. Similar to, I had a single qubit vector space where I used 0, 0, 1 Okay, and this is not subtraction, but 0 and 1 as the basis state for single qubit system. Not only 0 and 1, but I also had get plus and get minus, and I also had get I and get minus I as the orthonormal basis states for single qubit system. So I can use get 0. I can use for the 2 qubit system, I can use get 0 0, get 1, get 0 1, get 1 0, and get 1 1 as my basis state for the 2 qubit vector space. So that, which means I can, if I have a general 2 qubit state in some general superposition state, I can always represent that in terms of these 4 states, basis states, which will be a complete representation. Okay, so with that understanding, let's now revisit entanglement. So in the last session, I discussed about entanglement. Not only that, I told you about that there is an interconnected property between two particles, 2 qubits, situated at 2 different positions, maybe at a very vast distance, such as in our room or in a satellite. But what is the how do we understand this connectedness mathematically? So we can also explore this using these concepts of tensor product and try to see for ourselves that why the entanglement really happens between these two particles. What is the reason for it mathematically? So entanglement, when I discussed about it yesterday, I showed you this interesting state, get 0 0 plus get 1 1. And I told you that when I measure the first particle and found out it is in 0, then the second particle will be in 0 and cannot be in 1. And the same way, if I measure the first particle to be in 1, then I get the second particle to be always in 1 and not 0. So I'll first give a formal definition to entanglement. So here we have a quantum state get psi, and it is expressed in some vector space, represented in some vector space V. But the V is composed of n vector spaces, V1, V2, and Vn till so on Vn. And these V1 to Vn are individual single qubit spaces, single qubit vector spaces, whereas capital V is a multi-qubit vector space, and our ket psi is a multi-qubit quantum state. And now if I can express, if I can write ket psi as V1 tensor product with V2, tensor product with V3, and so on, tensor product with Vn, where V1, V2, and Vn, they are all single qubit states. That is the meaning of ket Vi belongs to capital Vi. So these are all single qubit states. Then ket psi is unentangled or separable. Or in other words, if I cannot express ket psi in this way, in this fashion, then ket psi is entangled. To illustrate this, let's take this example, the standard entangled state also has got a name, Bell state. And this is a maximally entangled quantum state. So if I can express this in terms of, so it is not denoted by ket 5 plus, and if I can write this in terms of 2 single qubit states. And how do we write single qubit states? A get 0 plus B get 1, right? This is a single qubit state. And there are two particles, two qubits. So I have to do a tensor product, because here V1, tensor product V2. So this will be C get 0 plus D get 1. Okay, now using the properties of tensor product which we saw in the last slide, we have to we can do a tensor product. We can distribute this tensor product. So it will be like A times C. So this 0, it will multiply with this 0. So it will be 0, 0. And again, this 0, it will also multiply with this 1. It follows the same properties of tensor product which we discussed in the last slide. Okay, so I'll just simply write get 0, 1. And now plus, now the next term, get B. Get B1, B into get 1. So B and B into get 1, B into C into get 1, 0. Okay, so, and the final one will be B times D, and it is 1, 1. Okay. Now compare this this whole thing with the original state, that is get 0, 0 plus get 1, 1. And now we have no terms corresponding to get 1, 0 and get 0, 1. Okay, right, I will use a different color here. Yeah, so for get 1, 0 and get 0, 1, we don't have corresponding terms here, which means that AD, this value AD is equal to 0, and also BZ is also equal to 0, because the coefficients must be equal to 0, because there are no such terms. But when if AD is equal to 0, either A is equal to 0 or D equal to 0. But if let's say A is equal to 0 and D is not equal to 0, then AC will also become equal to 0. And thus we will not get a corresponding term of 0, get 0, 0. But that is not the case, right? And if D is equal to 0, let's say, and A is non-zero, then BD will be equal to 0. Then we will not have a, as D equal to 0, we will not have a term of 1, get 1, 1 here. But we have a term of get 1, 1. So it simply means that it's not possible to write this particular state get 5 plus in terms of 2 single qubits, right? It's a, there's a meaning. Second, yeah. So we cannot write get 5 plus in terms of 2 qubits. It's not possible. It is not possible. And the reason is it is entangled. It is entangled. So that's how we understand the property of entanglement through mathematical means. And if we are given a state such as this, we can simply check whether it is an entangled state or not using this verification. Similarly, we have other 3 Bell states, which are also maximally entangled states. And these are represented as phi minus, psi plus, and psi minus. And phi plus is the is this first Bell state I have mentioned. And the superscript is simply whether it's the plus sign or minus sign. And the phi stands for wherever there is 0, 0 and 1, 1, both have the same parity. Where psi is when both are having different parities. Okay, so let's move to the next. So here we just test our understanding, whatever we learned so far. So we have a 2 qubit system here. And the question is, what is the matrix representation for this system? So we have 3 terms, 3 states superposing. the superposition of three states 0, 0, 0, 1 and 1, 1. And the coefficients are 1 by 2, I by 2 and 1 by root 2. So let's start working. So 0, 0 is, we know from the previous slide, it is represented as 1, 0, 0, right? And 0, 1 is, what is a 0, 1 representation? Let's go back and see. 0, 1 is, yeah, 0, 1, 0, 0. Right. So 0, 1, yeah, 0 and 0. And then 1, 1 is 0, 0, 0 and 1. Am I right? Let's see. Yeah, 1, 1 is 0, 0, 0, 1. Okay, so the coefficients are 1 by root 2 plus here I by 2 and this one is 1 by 2. So I simply do addition, that's it. So here this is 1 by 2. So the first element will be 1 by 2. And the second element from the second term we find that is it is I by 2. And then the third term gives me the last element. So what about the third element? Third element will remain 0 only. So here it is 0 plus 0 plus 0. It will be 0. And then the fourth element is 1 by root 2. So the normal addition of matrices, we get this as a matrix representation for this particular quantum bit, or not quantum bit, this particular multiple qubit system. Okay, now this is the second problem here. 1 by 2 get 0 plus root 3 by 2 get 1. Tensor product with 1 by root 2 get 0 plus I by root 2 get 1. Okay, so how do we approach this problem? So if we have in this Dirac notation, so these bra and ket notations are also called as Dirac notation. So we can simply use the properties of tensor products and write them as, so 1 by 2 get 0 multiplied with 1 by root 2 get 0, where that will be 1 by 2 root 2 get 0 and get 0. And then we multiply this with the second one. So that will be I by 2 root 2. And the ket values are 0 and 1, right? 0 and 1. And then coming to the second term, root 3 by 2 get 1. So it will be root 3 root 3 by 2 root 2 times get 1 and 0. And then the final one, which is root 3 I by 2 root 2. Okay, I'll make some space here. Yeah, so I'll just write it here. Root 3 I by 2 root 2 times 1 1. Yeah, and now we just need to do the expansion like we have done in this case here. So this is represented as 1 1 1 and all zeros, 3 zeros, 0 0 0 and this is represented as 0 1 is 0 1 0 0, right? So this will be 0 1 and then 0 and 0, and the last one is 1 0. No, this is the third one, not the last one. So 1 0 will be 0 0 1 and 0, and this one will be 0 0 0 and 1. Yeah, and then multiply with the coefficients. So I'll write the answer here. Okay, so when we multiply with the coefficients, we get 1 by 2 root 2 on for the first element here, and the second element I by 2 root 2. For the third element, root 3 by 2 root 2. Yeah, so it's a little messy here. Anyway, root 3i by 2 root 2. Yeah, so I got a quantum state like this. This is a matrix representation for my quantum state represented as this. So this is a very easy way to represent the Dirac notation, while the matrix notations are convenient for performing various operations and mathematical transformations and etc. So now let's move on to another a related topic, but another concept here. It's about quantum gates. So we are familiar with classical gates used for classical computations. We are familiar with, from our electronics courses, we know about the Boolean gates like AND gate, OR gate. AND gate takes two inputs and give out one output. And whenever there is one, if at least one of the inputs is 0, the output will be 0, otherwise it will be 1, right? And if for the one of the inputs of OR gate is 1, then the output will be 1. If not, it will be 0. And XOR gate is when it is also called as parity gate. It's quite important. So when both of the inputs are having the same value, such as 0 0 and 1 1, then the XOR gate outputs, I think it's 0. It outputs 0. If not, if they are of different values, such as 0 1 and 1 0, then it outputs 1. So that is about classical gate. And in analogous to that, we also have quantum gates, but on a different platform. But it is also called as quantum gate. And what it does is it transforms the input state into a different output state. So basically, it does a quantum operation which transforms the states. Okay, and this kind of operators are called as unitary operators. Why unitary operators is often denoted as U. Why it is called unitary is because we know from our so far, whatever we have learned from our journey so far, that the quantum states have probabilistic outcomes. And the thing about probabilistic outcomes is that the probabilities of each of the basis states, or the probabilities of obtaining each of the basis states, sum to 1, right? Unity. And so that is represented by mod alpha square plus mod beta square equal to 1, which you have seen. And so unitary operators always they obey a relation such as u times u dagger is equal to I. So I is the identity matrix, and u dagger is a it is a transpose conjugate of u. So yesterday I did discuss about what is a transpose conjugate. A conjugate represents if we have a complex number in our matrix, such as I, so that I becomes minus I, right? I becomes minus I, and the transpose represents the row vector becomes column vector, and column vector becomes row vector, just as in the case of bra and cat vectors. So what do they do in fact? So a Hadamard gate is simply, it makes superpositions. So if I pass a non-superposed vector state like ket0 or ket1, they get transformed into ket plus or ket minus, which are superposition states. So that's what Hadamard gate does. And and this is represented as you know, in a matrix form. It is represented as 1 and 1 and minus 1. Okay, yeah. So we will we'll come to that. So out of this 4 gates I have mentioned here, the easiest one to understand is a swap gate. Suppose I have a qubit line, another one here. So if I initialize the first qubit line as ket0 and the second line as ket1, okay, and then I have a swap gate here, which is represented like this, a very simple representation, to align with 2 x's at its terminals, connecting the 2 qubit lines which I wanted to swap. So what it does is, at the end of the operation, I get ket1 on the top and ket0 on the bottom. So this is a swap gate in quantum circuits. Next, I'll come to the C0 gate. Now, what is a C0 gate? It is short for controlled NOT gate. We are familiar with NOT gate from the classical computation. What does a NOT do? If I pass a 0, it becomes a 1, right? So it's something like this, I think. So I have, I pass a 0, I get 1. And if I pass a 1, I get a 0. Right, so this is the representation of the classical NOT gate. Similarly, a C0 gate is a controlled NOT gate. So I do a NOT operation, but I use a control bit to do that NOT operation. So similar to swap gate, here also I have 2 qubits, and I have so I have 2 qubits. One is a control bit represented by this thick knot here, okay, and another one is a target bit upon which the knot performs, which is represented by this hollow circle. So if I let's say if I pass a ket0 here and I pass a ket1 here, so what I get here is ket0 will remain ket0, but ket1 will also be ket1, because for a ket0 there is no operation being done per carried out. But if I instead of ket0, if I use ket1, okay, so instead of ket0, if I use ket1, then what happens is then the control gate gets activated and the 1 becomes 0. And this one remains 1. So that is the action of C naught gate. And I also have something called an X gate. Now, X gate also implies that there can be a Z gate also, and there can be a Y gate as well. Okay. Yeah, that's on the side note. But what is a ZX gate? X gate is simply is a quantum analog of a NOT gate in a classical computation. So it simply what it does is it takes a 0 and makes it 1, and it takes a 1 and it makes it 0. So it is a classical and a quantum analog of the NOT gate. Yeah, so it's just a NOT gate. So if I need to transform my ket 0 into ket 1, so what kind of matrix should X be? Because this is 0 is represented as 1 0 and 1 is represented as 0 1. So what should be my X gate to be? So X acts on this one 1 0, right? It acts on 1 0 and the result is 0 1. So if X is suppose let's say A, B, C, and D, then what are the values of those elements, those entries of X? Like we have a 4-dimensional matrix. So what should be the values? So we can easily see from this we can see that 1 becomes here it gets flipped, right? It gets flipped. So these two are 0, the diagonals are 0, whereas the off diagonal will be like this. So now you can check that 0 times 1. 0 times 1 would be 0 and 1 plus 0 is 0. So the first entry is 0, whereas the second for the second entry we multiply 1 with 1 and 0 with 0, so that is equal to 1. So I get 0 1. So X is represented as this way, 0 1 1 0. Okay, and X is a member of a family of operators or family of quantum gates called as poly gates or poly operators. Okay, so X is represented as 0 1 0 1 0, and there is Y also, which is represented as 0 1 minus 1 and 0. And we also have Z poly, which is represented as 1 minus 1 on the diagonals and 0 and 0. Yeah, sorry for this, it's not. So I have the representations for the poly, which we use extensively in quantum computation circuits for both for measurements as well as for quantum gate operations. And then there is a Hadamard gate. Okay, I have already mentioned that it creates superpositions, and Hadamard gate is represented as so H. It is represented as H, denoted as H, and it is represented as 1 1 1 and minus 1. Okay, I hope it's correct. You can verify it. How do you verify? If you act this matrix on ket 0, you must get ket plus. And what is ket plus? Ket plus is ket 0 plus ket 1 by root 2. You know, ket plus is 1 by root 2 1 1, right? We have seen in the previous slide 1 by root 2 1 1. So ket 0 is 1 0. So if I act this one on ket 1 0, I should get 1 1 1. So you can try that and see whether it is coming out to be correct or not. Okay, and these things, C naught gates, swap gate, Okay. So this internet interruption comes in between. So from yesterday's experience, I think it happens only twice in a 2-hour period. Okay, so no worries. Fine. So I'm discussing about the quantum gates here, and there is another additional gate which is not mentioned, which is called rotation gate. Okay, so right, and it is used in the Grover's algorithm implementation. Okay, so this is a sample quantum circuit. I have it's taken from one of the code routine. So here, what I am doing here is I have two qubits here. It's a 2-qubit circuit, and they are represented by a Q0 and Q1. And I am measuring this at the end and storing the data in a classical qubit. Sorry, classical bit. So why I use a classical bit is because once I measure the qubit, I get only one outcome. It will be no more in superposition, which can be stored in a classical bit, right? So the main attractiveness of quantum bits or qubits is that it can maintain superposition, and that leads to that leads to exploration of different pathways to reach your solution, and which results in things like quantum interference, like constructive interference and destructive interference, which will ultimately amplify the solution vector. So that's the beauty of qubits. And now here in this quantum circuit, what did I do here? So first I took my Q0, which is the zeroth or the first qubit, and I apply a H. H represents Hadamard. This is a Hadamard gate. And what does it do, Hadamard gate? It will transform the Q0 into a superposition, right? So something which is implicit here is that these are initialized. This Q0 and Q1 are initialized to get 0. It is an implicit here. And then I apply a Hadamard on get 0 of Q, which is Q0. And then I get here in this position, I get a superposition of get 0 and get 1. Okay. And then the next thing is I have applied this kind of a structure. So earlier I have shown this corresponds to a C naught, okay, controlled NOT gate. And what it does is, depending on the value of Q0, it performs a NOT gate on Q1. So if Q0 is 0, then it does nothing. And if Q0 is 1, it flips the Q1. Okay, Q1 was 0, get 0. And when I pass through this gate at this position here, what I get is I get something like, so the convention followed here is I write Q1, state of Q1 on the left side and state of Q0 on the right side. Okay, so Q1 was 0 initially, right? And after this gate, it will remain 0 for the first gate state, first term of Q0. Whereas for the second state, it gets flipped. Q1 gets flipped to 1 because the state of Q0 is 1. So this is the state I get at this point. And then I do a measurement on Q0. So it will measure 0 or either it will measure 1, and for Q1. And if the measurement of Q0 is 0, then I am getting a promise, an automatic promise that Q1 will be also 0, because from the state I get that information. On the other hand, if I get a value of 1 for Q0, that means the second measurement here, it will also give me 1. And this is what is this? This is the famous Bell state, which we have come across a few slides earlier. which is a 5+ state, right? Right. Yeah. So this is a 5+ Bell state, and this is the implementation of how to create an entangled Bell state. So you apply a Hadamard on one of the state, and a controlled NOT gate like this connecting the two states, and you get a Bell state, 5+. Okay, so this is a sample quantum circuit for your familiarity. So we will be taking questions in the end, and also your feedback and comments. So if you have any points, I request you to write it down so that we can have a fruitful discussion in the end. Okay. So next is about quantum measurement. So we have so far we have studied about qubit and how to represent the qubits, and then we studied about how do these qubits get transformed, how can we perform operations on these qubits, and how to final thing is how to measure these qubits. And now these are very fundamental aspects of quantum computing, because even if you are a theorist or if you are a experimentalist or a practical person, still you need to know about this fundamental aspect about qubit, because qubit is a fundamental unit of quantum computing, right? Now the final aspect of this is called quantum measurement, and here I'm just briefly touching upon this. So here I have a 3-qubit state. It's ket psi, represented as zeros, ket 000 and ket 111 with the following coefficients. Now I can perform something like a measure all kind of operation. It's just a routine in the Qiskit software development kit, where I measure all the 3 qubits. I measure them at a stretch, and normally under normal conditions, what we do is a partial measurement. We do not measure all of them together, all the 3 particles together, but rather we keep one or two, the other, we only measure one qubit and leave the other qubits as it is. So how do we represent the measurement when they are in a state of superposition, right? Especially. So what we write Z tensor product with X. So the first particle, for the first particle, we use Z basis to measure it. For the second particle, we use a X basis to measure. For the third particle, we use I. I means identity, do nothing. We don't do anything. So this is similar to a light beam, which has a particular polarization along some direction, and we keep a Polaroid. We keep some Polaroid which has a particular axis allowed to be transmitted through it, and we keep another Polaroid here which has a orthogonal polarization axis. Then we find that no light appears in the end, at the output. But now if I keep another Polaroid here with some diagonal axis, then what happens is the light beam which passes through the first Polaroid, it will have a certain projection along the diagonal of the second Polaroid, right? And when it passes through the third Polaroid, then a little bit of light will also have a projection of very low intensity along the horizontal axis. So we get some light here when we keep a third Polaroid. So interesting experiments which you can see this. If we take out this Polaroid out, then we see no light coming out. And if you put it in, we see that there is some light coming out, right? So same way, we can measure the quantum states using different bases They are called basis measurement. So I keep a horizontal axis Polaroid in the middle, and I'm able to see light, and I'm also able to completely vanquish the light. This is because the light has not absorbed or anything. It is still there, but because it's a quantum state, and quantum states have something called superposition. And superposition, because of superposition, there will be always some projection in um, some intermediate axis. Just like we have a vector space x and y, and I have a vector here v. So this v has a projection onto x, which we denote as vx, and it has a projection along y, which we denote as vy. So when we measure v using x and y, we get vx and vy. Now, if I measure v using a different coordinate axis, such as y prime, and x prime is along v only. Oh, sorry. And the x prime, which is along v. So when in this case situation, v does not have any projection on y prime. V is completely along x prime. It has no projection on y prime. So same way, when I took out the Polaroid, so that time light has no component along this horizontal direction. So there is no light. But when I kept the Polaroid, I am measuring it in another coordinate. So I get some light coming out. So same way, in the quantum measurements, when I use a particular basis to measure the quantum state, I get some value corresponding to the projections in that projections of the quantum vector space, quantum vector in that basis. And if I use another one, then these projections will change. Okay, so if I use a Z basis, then I'm applying it on the first particle, right? So this is for the first one, second, and I is the third one. So for 0, what is Z0? Okay, so what is Z? I have mentioned it in the previous slide, right? 1, 0, 0, and -1. This is the matrix representation of Z. And ket 0 is 1 and 0. And now this value is, this is equal to 1 and 0 only. It does not change the ket 0. So it will be equal to ket 0 only. Conveniently, we can write Z0 equal to 0. And what about X? So I apply X on the second particle, which is a 0. And we have seen X is nothing but it is a quantum analog of not gate. So X will flip the 0 to 1. So that's why the final output has 1 here. And I means do nothing. It's an identity operator. So it will remain 0. So the final output is 0, 1, 0. Now that is this. And now the second one is we are applying a C0 operator for the first, and then then this is the tensor product with Y. And there are 3 states, 1, 1, 1. But I have only 2 measurements. Okay, so why is that? Why is that? Because C0 is a 2-qubit operator. So C0 acts on these first two qubits, where the first one will be the control bit and the second one is the target bit. So when I apply C0 on 1, 1, let's see what happens. C0 is applied on 1 and 1. So if it's a 0, if the control bit is a 0, then it does nothing to the target bit. But if the control bit is a 1, then it flips the target bit. So here the control bit is 1. So it flips the target bit, which means 1 and 0. Hence we have 1 0 here. And the second one is Y. Okay, so Y acts on the third qubit, which is in the state ket1. So what it does, so Y is basically 0, 1, minus 1, and 0, right? Okay, so what it does, and 1 is 0 and 1. So 0 and 1, so it flips it, yeah. And 0 and 1 means it will be 1. So I think here it will be 1. And then minus 1 times 0, 0, and 0 times 0, it is 0, right? Yeah, so I get 1 0, which is equal to ket 0. Okay, so I get a third particle as 0. So this is how we apply measurements on the multiple qubit system. Okay, now these are Z basis measurements are very common, but we also have other measurement bases. Like I have already we have discussed the Y basis measurement and X basis measurement, C naught. There is other C naught is not a basis measurement. C naught is just a operator. But there are some other kinds of measurement like Hadamard. Hadamard basis is a valid basis measurement. So Hadamard is basically it measures in the basis of plus, ket plus, and ket minus. So these are the basis states for Hadamard. For the standard basis measurements, we use 0 and 1. For Hadamard basis measurements, we use plus, ket plus, and ket minus. So here the x and y, if x and y represents 0 and 1, then x prime, y prime represents plus and minus. And that is the Hadamard basis. Okay, so this is the basics of quantum measurement. And now there is some interesting in the remaining time. We will just discuss an interesting application of what we learned today. This is called an entanglement-based protocol. And this is a very famous protocol. It's a quantum teleportation. It's called quantum teleportation. So yesterday we discussed while defining the qubit that qubits have a very important property called a no cloning theorem. It's defined by a no cloning theorem. It simply means that if I have a qubit initialized in a particular state, alpha 0 plus beta 1 with a particular alpha and beta values, it cannot be cloned, or it cannot be copied and used to prepare another state with the same alpha and beta value. That is simply not possible because of certain mathematical reasons, particularly the unitarity conditions. However, what we can do is something called a teleportation. What teleportation means essentially is that if I have a quantum state with me, let's say it is ket V is what I have with me, and I can transfer this particular state or recreate this particular state at another location, the same quantum state ket V, but as soon as this state is created, I will lose the information about my state. It goes away. So when this creates, this goes away. They cannot simply simultaneously exist because of the no cloning condition. And this particular process is called the teleportation. And here is an implementation by which we can achieve teleportation. So there are certain steps where systematic applications of different quantum gates are performed, and we will see that how the states get recreated at other location. So a classic scenario is that there are two people, Alice and Bob, and they are situated at two distant locations. Now Alice has a quantum state prepared in the state ket V, and both Alice and Bob, they share an entangled pair, which means a single qubit QA is entangled with another single qubit QB, which is with Bob, where QA is with Alice. So that is the relation. And now Alice wants to send this gateway to Bob very securely, and basically it needs to be recreated with Bob, but she will not send the information of B by measuring it. If she measures it, she will lose the state gateway, right? She will lose the state because it will collapse into one of the basis states. So without measuring, she wants to send this to Bob, and Bob needs to recreate this state. So how we can do this mathematically, if we look at it, it is possible. And how we can do is, first of all, Alice needs to do certain measurements on her states. She has this ket V, a single qubit, and also ket QA. So there are two qubits in the possession of Alice. Whereas Bob has a single qubit, ket QB. So first so we have a multi-qubit system of V, QA, and QB, where V and QA are with Alice and QB is with Bob. Okay, so Alice performs a C naught first. Okay, so in general, from a global perspective, we are applying a C naught tensor product I on this system. So I simply means that Bob, the third bit, which is with Bob, we are not doing anything to it because it is with Bob. Only Alice is performing the measurement. It's a C naught. Okay. So what she does, if V is 0, she doesn't do anything on QA. But if V is 1, then she will flip it, right? So basically, she's not measuring V and changing QA. That's not the understanding here. But she applies a C naught gate. Okay, so the C naught gate, without measuring only, it will do the flipping operation. And once that is done, then she performs a Hadamard on V, and she does nothing on QA and QB. Okay, and after that, she will get a state, right? A state, she'll get a final state after this. She measures it in the Z basis, and she will get a particular outcome. It will be in one of the 2-qubit bases, either 00 or 001, 01 or 10 or 11. Any of the 2-qubit bases she will get as an outcome, and that is sent in a classical channel. So these values are classical values. It'll either get 00 or 10 or 01 or 11, and that will be sent to Bob. And when Bob receives this information, the classical information of Alice's measurement outcome, he does certain decoding protocol procedures. And using those decoding procedure, which depends on the information sent by Alice, he will be able to recreate ket V by performing certain unitary operations on his qubit QB. So this QB will get transformed to ket V after certain unitary operations performed by Bob. Okay, so it's a very interesting calculations. I think we have 10 more minutes, so I can just give you a brief. I can quickly do the calculation, and then we are done. We are done for today. Can open for questions and doubts and clarifications. So, so how we do this is we have let's say the QA and QB are bell states, which is in 0 0 and 1 1. Okay, and Alice is having a state vector alpha 0 and beta 1. Okay, so this is tensor product, these two states. Give me a second. Yeah. Okay, so what we get is after the tensor product, alpha, so alpha times 0 0 0, and then alpha times 0 1 1, and then we have beta times 1 0 0, and beta times 1 1 1. After this, Alice performs a C0 operation on the 2 qubits. Specifically, it's a C0 tensor product I. And what it does is if the first particle, first qubit is a 0, then the second qubit is not changed. And if the first qubit is a 1, then the second one is flipped to 1. So that results in alpha 0 0 0. So here is a 1 by root 2 here. So I not mentioned it. We'll add it in the end. And then the second term will be alpha times 0 1 1. Okay, yeah. And then the third term will be beta times 1, and instead of 0 it will be 1, and then 0 it will be flipped because the control bit is 1, and the last term is beta times 1, and then this will be 0 and then 1. Yeah, so this will be the state after the C0 application. Then after she does the second operation, which is what which is first she did a C0 I, and then she did a H Hadamard and I. So she does a Hadamard operation on the first qubit, this qubit. So what it does is it creates a superposition. So it turns this 0 into a superposition of 0 plus 1. So we will get double the terms now. So here after this Hadamard So I can just write H I I. Okay, it implies tensor product is not shown here. We are applying header mode on the first quantum bit and doing nothing on the second and third. So this will result in alpha 0, 0, 0 plus alpha 1, 0, 0. And the second one also the same happens. It will be 0, 1, 1 and plus alpha 1, 1, 1. And then the beta terms, beta 1 becomes 0 minus 1, right? So 0, 1, 0. And the next term will be minus beta 1, 1, 0. And the last, expanding the last term, beta 0, 0, 1 minus beta 1, 0, 1. Okay. Yeah. Okay. So, so this is the final state after her final measurement, and then after that there will be after her final transformation, not measurement, and then finally she does a Z basis measurement. Z measurement. So what it does is we will segregate all the first two indices. So here ket 0, 0. Ket 0, 0 comes here and it comes here also, ket 0, 0. So we will take ket 0, 0 outside. Okay, and then there will be alpha times ket 0 plus beta times ket 1. Correct? Alpha times, and then the third one, ket 0. And then beta times the third qubit, ket 1. Because we have taken the first two qubits outside. Yeah. And then plus, next what we do is, we'll take 1, 0 out. So we take 1, 0. And here we get alpha times, okay. Ket 0. And where is the other 1, 0 coming? It's coming here. It is minus beta times ket 1. Then the third one is ket 0, 1. So I take ket 0, 1 out. And then alpha times ket 1. And the other one is ket 0, 1 is coming here, right? So beta times ket 0. And then finally, I take ket 1, 1 out. And that results in alpha times ket 1. And then from here, minus beta times ket 0. So then Alice measures in one of these Z bases, and then she sends that qubit information in a classical that the measurement outcome of the qubit in a classical line, maybe through some telephone call or something like that, telegram message or email message, she sends the values of the classical bits. It would be either 0010 or 01 or 11, and that is received by Bob on the other side. He gets either 00 01 10 11, and then if he gets a 00, then he does nothing. He keeps the qubit as such with him. Okay, which means the entangled pair which he has, ket qb, okay, it will be in the same state as that of ket v. Okay, it will be equal to ket v, so he does nothing. I. Okay, from this mathematics we will understand that it will be equal to ket v, and then he does a x measurement if he gets a 01 bit received. Okay, so yeah, so something's missing here. So the value will be alpha 0 minus 01, right? 01 means alpha 1 plus beta 0. So this will be 0 here, and this will be 1 here. And he does a decoding, and then he gets the value of v. He gets ket v. How come? When he does x, so he is flipping this 1, he flips it to 0, and he flips the 0 to 1, and he gets ket v. He recreates the original state. And if he receives 1 0, 1 0 is here, then the state vector he has is alpha 0 minus, this will be minus, and beta 1. So he simply does a z measurement on his entangled pair. And what happens, it will flip the sign. So this minus becomes plus, and he gets ket v. And if he gets 1 1, then he will he does a y, and it will flip the sign and as well as the bit, both. So this was originally alpha 1 and beta 0 and with a minus sign. So he gets a ket v here when he does a y. So that's how he successfully recreates the state, quantum state, which Alice had in such a way that it gets teleported. It destroys the original state of Alice. Alice lost the state because she did the measurement, and then it gets recreated on the side of Bob. Bob gets the exact same state without violating the no cloning theorem. So this is a protocol of quantum teleportation. It gives you a clear idea about how we have utilized whatever we have studied in this session and last session of the principles of superposition, entanglement, tensor product, and measurement, quantum gates and measurement. Yeah, so with that, I will end today's session. So I think we can open questions and comments, if there are any. Okay, so one question is, I think it can be 1 by square root of 2 in case of first exercise. Okay, so which was that? 1 by square root of 2. Okay, so I think you mean somewhere here, right? 1 by square root of 2. Yeah, so there should be some terms here, factor of 1 by root 2, because otherwise this is not a valid quantum state. 1 minus 1 is not a valid quantum state, because it simply means that this vector is not unitary, or it is not a unit vector. Every quantum state vectors are supposed to be unit vectors. So if we multiply it 1 by root 2, then it becomes unit vector. Then it becomes unit vector. So here also 1 by root 2 is missing. So yeah, thanks for pointing out that. Another question is, can we get the notes? So I'm sorry, I don't know which notes you. I don't have any notes as such. I mean, these are like slides. I think some of them are like maybe available in the LMS. So I think you can contact the support team regarding the notes or slides. As I was saying, there are three things, right? So mainly two things. There's a hardware and a software for any computers, right? So we will be focusing on both software and hardware. And what we discussed today and yesterday were the fundamentals. And tomorrow we will delve into the software part, mainly the algorithms and all. And day after tomorrow, we will focus on hardware. So we'll kind of cover both in this course. And final day, we will have some applications. Yeah, it's a very good question by Subramaniam. He asked, let me know the books where I need to start learning from basic level. So I love one book. It's written by Riefel and Pollack. It's called A Gentle Introduction to Quantum Computing. So that is a very good book to start from the basics. Yeah, you're welcome. So I see someone has raised a hand. Okay. Yeah, sure. Nagarajesh, I will text the name of the textbook. In a second, I'll just confirm the name. Quantum Computing, a General Introduction. You're welcome.
Okay, sir. Like, if you don't have any questions to be addressed, we will wind up for the day. Any other questions? Okay, I hope there is no questions to be addressed from trainer. Fine. So we will all wind up for the day. We'll meet again by tomorrow at 3 p.m. So, dear faculty members, it is just a reminder. Please mark your attendance without any fee. Okay. And one more important thing, if you mark your attendance from one mail ID, kindly mark your attendance with the same mail ID every day. All the 5 days you have to mark your attendance only one particular mail ID. I'll be sharing the attendance link once again on the chat. If you have missed out to mark, kindly mark your attendance. And some are asking for yesterday's attendance link. Yesterday's attendance link will be not active as we already informed. The attendance link will be active only between 4:30 to 5:30. So yesterday's link we can't share. And related to LMS, so the LMS, whatever the materials, it will be uploaded in LMS. Kindly wait. all the materials you can watch it, like recordings and materials you can view in the LMS. And LMS access, if you guys still have not received the mail, please be waited. Within 24 hours, you will receive it. And whatever the LMS access, if you have not received, it will not affect your attendance. As we told, whatever the live session which we are running, in the same live session, we are sharing the attendance link every day. Please mark your attendance without any fee. So if you secured 60% or above 60% of attendance, for definitely you will receive the certificate. Yeah, I just now informed Nagaraju sir, please be waited. If you have not received LMS portal link, you will receive it within 24 hours. The LMS will be used for the recordings and also for the materials. Don't be worried. Like it will not affect your certificate because the attendance link you will be marking in a live session, right? So, and one more thing, those who are attending, like the students won't get the certificate. This is the faculty development program. So the student can join this particular program, but just for their knowledge purpose. So the student will not get the certificate. Okay. Sai Kumar sir, I just now informed day one attendance link can't be shared. I'm so sorry. Okay, I hope you all clear. So we will wind up for the day. Thank you all. Thank you for joining. We'll meet again by tomorrow at 3 p.m. Thank you, everyone.